Hello, class. So on this video, we're still on section 3.5, like method of undetermined coefficients. So in the previous video, we saw what the general process was to find a form of the particular solution. It was pretty straightforward, right? It was basically look at the right-hand side, right? So the function that's on the right-hand side, g of x, take and include on your particular solution all possible terms that arise from derivatives of g of x. And of course, you always include unknown constants or undetermined constants in front, right, so that we have some degree of freedom into choosing the right constants afterwards, after we plug it into the ODE, so that the solution actually works. Right? And we did this not explicitly, but it matches what we did in the first two examples, right? So if you want to go back and think of it this way, you should see that you get the exact form of solution and that everything else works. And then we did an example here where we're like, okay, suppose that the right-hand side is g of x equal to e to the x sine x, right? And then we wanted to find a form for y of p. As we saw in the general process, y sub p has to include all possible terms that come from derivative of g of x, right? So we went, and I showed you here what you generally want to do. You don't want to take infinitely many derivatives of g of x, right? What you want to do is take as many derivatives until you realize what the pattern is, and you say, okay, I know now that these are all the terms that are going to arise no matter how many derivatives I take. And in this case, it turned out that the first derivative was enough to know that. Right, so the only terms that were going to arise were e to the x sine x and e to the x cosine x. So I write my particular solution to include those with the undetermined coefficients in front. Now, as I mentioned in the end of that video, there's one caveat. So this process, this particular solution is always going to work. You're always going to be able to solve for A and B with one exception. But we can take care of that exception pretty easily. Okay? So I'm going to show you what the exception is, right, in this example. Okay? So let's go ahead and solve this ODE. Right? It's second order, linear, non-homogeneous. We've done this now. This is our third time, so let's just go ahead and do it. Right? Find the characteristic polynomial. Right? For the homogeneous case, so this is going to be r squared minus 5r plus 4. Set it equal to 0. Okay. And hopefully this factors. If not, just use the quadratic formula, but I think it does. Yeah, I think it's r minus 1 and r minus 4. Right. So from this, we get the general solution, c1 to the x. So 1 times x is just x, plus c2 e to the negative 4x is the general solution. Okay. Now, let's go ahead and find the particular solution. Now we know exactly what to do, right? Just take derivatives of g of x, right, the function on the right-hand side, and make sure to include all possible terms that arise from those derivatives in the particular solution. So let's do it. So y sub p is what we're going to find. G of x is, for us, 8 e to the x. So in this case, it's pretty obvious, but I mean, if you're not convinced, take one derivative, and you just get itself, right? So no matter how many derivatives you take of g of x, you're only going to get 8 times e to the x, right? So the only term we have to include is e to the x in our particular solution, right? So we're going to include a constant times e to the x. Now this should work, right? We could just plug this in, and we should be able to solve for a. I'm going to give you a moment and think about why this is a problem. And I'm going to give you a little hint. I mean, of course, you can just pause the video, but I like the dramatic effect of telling you. But relate those two things. And remember that y of x above is the solution, general solution for the homogeneous case, right? The homogeneous case. Remember what that means. Okay, so I think that's enough time. And again, you can pause the video if you want to think about it more. But notice that the particular solution here is part of the general solution. For example, if you let C2 be equal to 0 and C1 be equal to A, in the homogeneous case, or in the general solution for the homogeneous case, well, then you see that that y sub p is a solution to the homogeneous case. Right? Why? Because if you go to y of x, replace C2 with 0, C1 with A, right? Remember, the general solution of the homogeneous case holds for any choice of coefficients, no matter what C1 and C2 are. So if you let C2 be equal to 0, C1 equals A, what does y of x become? Right? So y of x becomes a to the x, meaning that without plugging y sub p in to the ODE, I already know that the left-hand side is going to be 0 by definition. That's what it means to be a solution to the homogeneous case, right? You get 0. And that's a problem for us because we don't want to get 0. We want to get 8 to the x. So this is the one thing you have to be careful. This is the one precaution. You have to make sure that the terms you use in y sub p are not solutions to the homogeneous case. Again, because if any of those terms is a solution to the homogeneous case, it's going to go to 0. You're going to lose whatever constant you had in front as a degree of freedom, and it's not going to work. Of course, here I'm working with only one term, so it's the simplest case, but hopefully it's illustrating what the problem is. How do you fix it? Well, the solution is actually really straightforward, like very straightforward. So let me write it in another color. Oops. What did I, oh, yeah. Okay, so what's the solution? So, or fix, let's call it a fix. What's the fix? Multiply any term of y sub p by x, just the function x, as many times as necessary until that term is no longer a solution to the homogeneous case. For example, in this case, our particular solution was y sub p equals, so let me write it again. And for this example, y sub p was a to the x. The general solution for the homogeneous case was, let me do it in purple, was y of x equals c1 to the x plus c2 to the negative 4x. Right? And it doesn't matter which one is c1 or c2, right? Because they're arbitrary. So how many times do we need to multiply? And again, we only have one term this time, but it works in general. How many times do we have to multiply our term by x so that it's no longer in the general solution? Well, if you see, we only need to multiply it once, right? Because once we multiply it once by x, it's no longer of this form. So implies if we change y sub p for y sub p equals a times x e to the x. And that's the fix. If you use this as your guess, it's going to work out. And it's no longer going to be 0 because it's no longer a solution to the homogeneous case. And it's as simple as that. Anytime you see a term in your particular solution that's already or included in the general solution for the homogeneous case, just multiply it by x as many times as needed so that it's no longer in the homogeneous, in the a solution to the homogeneous case. So I'm going to do that in general. So summary on how to fix the problem in general, if you have more than one term. So I gave you an example where the particular solution had only one term. So let's see in general if your particular solution has more than one term. So let y of, so given a second order linear non-homogeneous ODE with constant coefficients, right? We already know it looks like this: ay double prime plus by prime plus c equals g of x, where g of x is not equal to 0. Let y of x be the general solution to the homogeneous case, right? Now, suppose y sub p equals f1 plus f2 plus f sub k of x. So we have k terms, right? So the f sub i's are the k terms. Now, anytime, so I'm just going to summarize, anytime f sub I of x, so where I is 1, 2, 3 up to k, any of the terms, so anytime f of I of x, or which just means any term, is included in the general solution of the homogeneous case, you're going to replace it with, let's use another color. Replace it with f sub I x times x to the m, I guess. We could use m. So replace it by x to the m, where m is the smallest positive number, for which x to the m f sub I of x is not in the general solution. Right? So that's how you would write it mathematically. Right? I'm giving you a mathematical expression. All this means is multiply it by x as many times as needed until it's no longer a solution of the homogeneous case. And I'm going to write it in the more layman terms. So in other words, multiply fi of x by x as many times as needed, so as many times as needed, until f sub I of x, times x, until it's, okay, so let me not write it like that, until it is no longer in the general solution of the homogeneous case. That's what we do. So if there's more than one term, check that each term is not in the general solution of the homogeneous case. If it is, it's multiplied by x enough times until it's no longer in the general solution. Okay. So let's do one example. And then that should be good and again, that's the only thing you have to worry about. So this would be example 4, right? So suppose that the general solution for a second order linear. No. Let me write it differently. I think if I write it like that, it's gonna sound a little bit confusing. So given ay double prime plus by prime plus cy equals g of x, with g of x not equal to 0, right? So suppose, I'm just gonna do it now, suppose the general solution to the homogeneous case is given by, so let's do something, let's do something like this. Y of x equals c1 e to the 3x plus c2 x. And again, I'm just pulling this, out of nowhere, right? So it's just, now I see that these are not linearly independent everywhere, but they're linearly dependent on some interval, right? So on some interval I. Right? And then furthermore, suppose that after taking derivatives of g of x, right, the right-hand side, you get the terms. Let's do e to the x, e to the 3x, x, yeah, and x. Right? What is the choice of a particular solution that works? Okay. Right, so we're given a second order homogeneous, non-homogeneous ODE with constant coefficients. I'm telling you what the general solution of the homogeneous case is, and I'm telling you what terms arise from derivatives of g of x. Right? So given that information, what choice of y of p works? Well, originally, right, we would try y sub p is just, we would include all those terms. Right. However, notice that both e to the 3x and x arise in the solution for the homogeneous case. So what do we have to do? Multiply each of those terms by x as many times as needed until they're no longer part of the homogeneous solution. So this one does not work. But again, by the fix that I gave you, all you do is multiply by x as many times as needed. Right? So e to the x is not in the general solution of the homogeneous case, so that one is fine. E to the 3x is, but if I multiply it just once by x, it's no longer in the solution for the homogeneous case. Now the same with x. X is in a solution for the homogeneous case, but as soon as I multiply x once by x, so I get x squared, it's no longer in the solution of the homogeneous case. So I get C3 x squared. Oh, and I don't know why I changed the names for the coefficients. I was using capital letters, so let me stick with that. So let's do A, B, C. And I do it like this. Obviously, the names don't matter, but it's just so that it's easier to distinguish between the general solution of the homogeneous case and the particular solution form that we're trying to guess. Okay. So this works. Again, all we did was check each term separately. Anytime a term is included in the general solution of the homogeneous case, multiply by x as many times as needed. And again, that's the only issue that you're going to find. So as long as you check that, you're good. If a term is in the solution of the homogeneous case, multiply that term by x as many times as necessary, so that it's no longer in a solution to the homogeneous case. And that's it. There's one more topic to include in this, to cover in this section. It's not so hard. It's related to the superposition principle, but really this is the meat. If you can do this, you can do any problem in this section. What the next video is going to be talking about, which I already mentioned, is related to the superposition principle. It's just a way to make it a little bit less work if your g of x is very complicated. Like, what if your g of x has 20 terms, right? Then how do you make the process of finding all terms in that derivative easier? That's what we're going to see in the next video. But if you understand this, you're good for this section, okay? Because this is the meat for it.